Hi, I'm Marshall Styczinski. I'm a postdoc at the NASA Jet Propulsion Lab and an affiliate of the Europa Clipper science team. Now, I don't speak for the mission, so all of the scientific opinions that I'll be giving you today are my own and not representative of the mission. Now, I study icy moons, and the reason why I study icy moons is because they're a promising candidate for the search for life elsewhere. They're common throughout our solar system. All of the giant planets have at least one, and most of them have several. And there's such a common environment that has habitability potential that we think they could also be common in other stellar systems beyond our solar system. So they're certainly an important topic for study. And because most of them lie outside of what's considered to be the habitable zone, where liquid water is stable on the surface of planets, they give us a chance to extend the concept of the habitable zone and say it may be a little too naive to just look at the surface of the planets. And it might be important to also look at the subsurface too. So there are numerous icy moons throughout our solar system that are important topics for study. And the main reason why we think they are potentially habitable is they likely have liquid water, but also they may have water-rock reactions, where chemical reactions, where you have water in contact with rock, could support microbial communities there, as they do on Earth. We have lots of examples of hydrothermal vents on the Earth where chemical reactions provide not just heat into the ocean and warming a pocket around, but also metabolic inputs. So things that microbes can eat in order to sustain their metabolisms and provide the base of a food chain. On Earth, we have thriving microbial ecosystems around hydrothermal vents. And so it's reasonable to expect that such a thing might be happening at the seafloor of icy moons as well. On Earth, though, it's relatively easy to get a combination of reductants, which are commonly put into the water from these water rock reactions like hydrogen gas, along with dissolved oxygen in the water. So you have the potential for a redox or oxidation reduction reaction that is useful for metabolism for microbes. On icy moons, it may not be as easy as gas dissolving from the atmosphere because they don't have an atmosphere directly in contact with their ocean. So it may be important to have things like plate tectonics that can cycle material from the surface of these bodies down into the oceans. But we don't really have strong evidence that that materials are getting all the way from the surface down into oceans yet. But that's thought to be one potentially important source for providing habitability of environments in subsurface oceans. Now, I'm going to be telling you quite a bit about Europa, but I also want to include a bit of some honorable mentions elsewhere in our solar system, including Ganymede, another moon of Jupiter, Enceladus and Titan, which are both moons of Saturn. So Ganymede is a very large moon. It's the largest terrestrial moon in our solar system. It's even larger than Earth's moon. It's even larger than the planet Mercury. And Ganymede is so large that it has lots of ice and water at its surface, so much so that at the lowest layers of its ice and water near the surface, it has exotic forms of ice. So forms of ice that are actually more dense than the liquid water. And those sink in the ocean and can potentially stifle those water rock reactions that are very important for habitability. Now, we don't really know exactly what's going on deep in the interior, so further study is warranted. And for Enceladus and Titan, moons of Saturn, there are similar unknowns that are important for considering habitability there too. Titan is another very large moon, and it likely has a subsurface ocean that has similar conditions to Ganymede. And Enceladus, we have evidence of hydrothermal reactions from plumes that are spewing out of its south pole that the Cassini mission has flown through and taken samples of. Now, setting those aside and coming to Europa, I study Europa primarily, and the reason why we're sending missions back there is because Europa is really the prime example of potentially habitable icy moons. And a lot of why we know that is because of the Galileo mission, a mission that orbited Jupiter and made numerous flybys of Europa around the turn of the century, the 21st century, that is. And through gravity measurements and imagery of the surface, we are able to get bulk density. And the density of Europa is consistent with silicate rocks mostly, and with a layer structure from laboratory analogs, we can infer that has about 100 kilometers thick, so about like 60 to 80 miles thick of ice and water close to the surface. From reflectance spectroscopy, we also know that the surface is mostly water ice, but also with some salts that could be emplaced from Io, another moon of Jupiter, or brought up from the surface if plate tectonics are doing that on Europa, brought up to the surface from the ocean. So it could be a sample of what is in the ocean that we are able to measure at the surface. We're not quite sure yet. But we also, from magnetic measurements, have a very strong piece of evidence that Europa has a subsurface ocean. And that's because we see a large electrically conducting material. That's what the magnetic measurements show. And the best explanation for that material is that there is salty water in the subsurface of Europa, fairly near to the surface, so within about 15 or 30 kilometers of the surface. And that's because rocks and silicate rocks typically have quite low conductivity. So the best explanation we have for the magnetic measurements we've made of Europa is that there's a salty liquid water ocean. So we have pretty strong evidence overall that water rock reactions are happening in Europa, and the water and ice layer is not thick enough that there would be high pressure ices at the bottom. And so there's almost certainly water in contact with rock. And that's promising for Europa's habitability. That brings us to the Europa Clipper mission. So the Europa Clipper mission is run by NASA, and it'll be launched sometime within the next decade. And it has goals relating to characterizing Europa like never before, with the intent of understanding habitability of the environments on this moon. And it's going to make these assessments by numerous flybys of Europa. And the reason why we're not orbiting Europa is because it's a high radiation environment. Jupiter traps a lot of charged particles that can damage the spacecraft if it hangs out there for too long. So there are multiple flybys planned where we get in close to Europa, gather data, and then get far away from Jupiter quickly so that we can radio back the data without being in a high radiation environment. So we get the chance to take lots and lots of data, and also the chance to send back lots of data as well without damaging the spacecraft. And Europa Clipper is making these characterizations by way of 10 different directed science investigations that I group into 3 categories. And one of them is to understand the materials that are lofted to altitude around Europa and also present in its ionosphere. Another is to analyze the surface conditions using imagery and spectroscopy so that we know what's there and kind of what the history is, what's going on. And then also to characterize the subsurface layers and the conditions those layers are under, like the chemical and physical conditions, through using ice penetrating radar and magnetic measurements, among other things. So all of this is intended to give us a better idea of how habitable Europa's subsurface ocean is, and whether or not there may be other habitable environments, for example, ice brine pockets within Europa's ice shell. Now, Europa is not the only target for study that's promising from an astrobiological context in our solar system. There are other moons and other missions intending to target those moons. So one example of that is the JUICE mission, which is run by the European Space Agency. And JUICE stands for Jupiter Icy Moons Explorer. And it's going to have multiple flybys of Europa and Callisto on the way to orbiting Ganymede. And it has similar goals for Ganymede as Europa Clipper has for Europa. So trying to better understand the habitability of Ganymede. And eventually JUICE is going to orbit that moon. So we'll gather lots of information. We also have plenty of information about Titan and Enceladus from the Cassini-Huygens mission. We even landed a probe on Titan, that's the Huygens probe, and we have learned a lot about these moons and gathered evidence that they likely have subsurface oceans, but we've raised as many questions as we have answers. So we really don't know very well whether or not any of these moons is habitable, but we have pretty strong evidence throughout the solar system for liquid water oceans, including as far out as the moons of Uranus, Miranda, and Ariel, which show some signs of geologic activity and could have subsurface oceans. And even Pluto, as far out from the sun as it is, could have a subsurface ocean. So we see that the solar system is full of mysteries. And solving these mysteries can help us understand not just our own stellar system, but also other stellar systems far beyond. We haven't yet found evidence of life beyond Earth, but we're just beginning to scratch the surface on understanding the habitability and history of the bodies in our own solar system. And we know that life got started here somehow, so it's plausible that similar conditions may have been present on icy moons in their past or today. And that can be extended to icy moons beyond our solar system. Really, the evidence is out there, and it's just waiting to be discovered. It's up to us to discover it.